Here I have my first Kinetics Quiz for Engineering 2030 at Slick. Problem number one, we have a rocket is launched upward. Height was 33.9 feet at the end of the thrust portion, so that means up until this point, that is 33 feet. I have that as a y0. So that just means there's a force being acted on it, pushing it up that way. Or pushing the rocket, up. And then the rocket lands 11.4 seconds later. The rocket freely fell to the ground after reaching its maximum height. I'm assuming no air resistance, which leads to a constant acceleration, because we don't have anything other than gravity given to us. So that allows us to use any of these kinetic or kinematic equations. So the question we're looking for is, what is the speed of the rocket at the end of the thrust flight? So, as I pointed out earlier, y0 is this. That's where we, end our accelerated portion, where it is then in free fall, or no forces other than gravity are acting on it. And what you can do, free body of that before thrust going up, pushing it up, and then we still had gravity coming down. So we take thrust out of it, and we are only accelerating downwards after the thrust is gone. So, and assuming constant acceleration, so this is fairly simple, because all you have to do, or we are given the time already, with this second kinematic equation, this can be used for x or y. You just have to make sure you change things out. But as I'll show you, we already have the time. We have the acceleration. That's just gravity. We have the time again. We do not have the initial velocity, or the velocity at y0. And we have y0, which is the starting height, which is 33.9 feet. I have that right there. Our final y is 0 feet. So, and we know it takes 11.4 seconds to reach the ground later. That's where our final y is equal to 0. So, very simple here. Just plug and chug, rearrange some things, move all the constants over, or define variables over to the other side, and divide by 11.4, and we single out our initial velocity, or v0, and we get 186.5 feet per second. So, again, I don't see anything more complicated than that there, so that was fairly simple to me. I believe so. And then for problem number 2, we have another rocket launched upward. The height of the rocket was 70.4 feet at the end of the thrust and had a velocity of 237.1 feet per second. The acceleration of gravity, and the same as before, 32.2 feet. I guess it should also be important to note that that's considered the positive direction as well. And anything moving this way is also in the positive direction. So, no, it's given. But, and then we are looking for the maximum. We are looking for the maximum height of the rocket. So, looking for the maximum height of the rocket, we know that at the tip top of a velocity, or I don't know, we could say height over time graph, or a position function. Let's just put this as y, and then t, y in t, y in feet, t is in seconds. And we know that, say, dy over dt is equal to velocity, so the instantaneous radius at any of these points is the velocity there. And as you can see, with our parabola that we have there, that is going to be our max height right there. And what you notice about the max height is that it is the slope at that point is equal to 0, so that means the velocity equals 0. So that is where we are looking for v equals 0 to get the max height. So again, assuming a constant acceleration, we can use this top kinematic equation. And we have v equals v0 plus at. We have v0, we have a. We also have the final v there, v we're looking for, which is 0. Initial velocity 237.1 feet, and then negative 32.2 feet per second squared for gravity. We plug and chug. We get t equals 7.36 seconds to reach the maximum height, or for velocity equals 0, which means we reached our maximum height. So now that we have the time it takes, we can use the same equation as before. This guy, y equals initial plus initial velocity times time plus 1/2 acceleration times squared. So we have all of these variables on the right-hand side, so it's just plug and chug, and we get the maximum height being 943.3 feet. So again, fairly simple, a little more complicated than question number 1 because we had to find the time, but again, assuming constant acceleration, being able to use the kinematic equations is very, very easy.